Hello and welcome to Statistical Thinking in 5 Easy Graphs. I'm Mark Williamson for Transcend's Professional Development Core. This is a short video for the short video series. So, the goals of this short video is to talk about 5 sort of statistical thinking patterns that are summarized in common graphs. So, we're going to look about how data exploration should come first. Really, when it comes to statistics, it's all about a signal to noise ratio. Another goal, another of those statistical thinking lessons, is that assumptions matter. Fourth is that there are perils in confounding information. And finally, that clarity is actually better than cleverness. So those are the statistical thinking goals. Let's get into the graphs. So the first graph, looking at data exploration, is going to be the scatter plot. Because really, yeah, when it comes to statistical thinking, you have to understand your data, and that starts with exploring your data, not necessarily jumping right to a model to test things, but to see what your data looks like, to understand the nature of it, what sort of relationships might be there, what sort of difficulties might be there, and certainly different data will have different exploratory plots. If you have groups, you're probably going to do bar plots or box plots. But I think a scatter plot will be a good example to start with. That's for numerical data. And so that's a great way to see how two numerical variables relate to one another. So a simple scatter plot like a y versus x, you can start to explore and get an understanding of what might be going on here. Now, I actually simulated this data, so I have a known correlation. So these are sort of lightly correlated. And even just from exploring this, you see it seems that there might be some positive correlation. Now, if I simulate data with a stronger correlation, you can see it in this graph here, you really start to see a stronger trend. And you can, in fact, if you have some experience with data analysis, you might even be able to start to sort of eke out in your mind where the best fit line might be. And of course, if you have a very strong correlation, that becomes very evident. But how related your data looks with your test really starts with data exploration, and then moving on to looking at assumptions, looking at other things, and then finally run your model. But a good piece of statistical thinking is look at your data, make sure you understand it. So then when you're later doing statistical tests, that you understand that you're doing it right. Your analyses comport with what you see with your eyes. All right, next piece of statistical thinking is signal to noise ratio, because really that's what ultimately what a statistical test is you're generating some sort of test statistic, which is going to be a signal to noise ratio, which is your signals, and maybe it's a difference between means, and then the noise, which will be how variable the data is, like what's the standard deviation. So I think a box plot is a great example of this. And so here's just some fictional data here of a couple different groups. And I've again simulated this so that group A has a mean of 10 and a standard deviation of, I believe, 2.5 or 5. And I think it's 2.5. And then group B has the same standard deviation, so the same noise, but the mean is twice as much. As you can see that the signal is fairly strong between the two. There's a pretty big difference between group A and group B, and the noise is relatively reasonable so that you can easily sort of detect that difference. Whereas group C actually draws from the same mean distribution. It's not quite the exact same mean, but it's drawn from a distribution with a mean of 20. And so groups B and C essentially have the same mean, but then I bumped up, I think, the standard deviation to almost like 15 or something like that. So it's very noisy data. And you can see that with the bar plots being a lot wider. In fact, that makes it even much harder to tell whether group C is really different from group A just by looking at it. Now, obviously, you'd have to do the appropriate statistical test to generate a test statistic and then look at that, whether that's has a significant p-value or not. But that's a lot of what goes into a statistical test. It's not just ANOVA, it's not just t-tests, kind of like what we see here, but even with regression, where you're having a value like a t value or an f value, and then and that's going to be a test statistic, that's going to be a signal to noise ratio as well. So I think box plot is a great example of that lesson, that statistical thinking ideal, that really what you're looking at can be boiled down to a signal to noise ratio. All right, third one is assumptions. So assumptions matter. And I think a great graph that helps showcase that is the histogram. Because for any statistical test, it has a certain number of assumptions that your data needs to meet. Otherwise, the test isn't valid. It could, so if you find a significant value, it's suspect if you didn't meet the assumptions. Now, of course, it could still be significantly relevant, but it's sort of suspect. Just like you could go to a dentist, who doesn't have his license. He could still do a good job, but going into it, his ability to do a good job is sort of suspect because it doesn't meet the assumptions of like having a valid right to practice dentistry. And so histogram is a great way to look at one of probably the most relevant or the most talked about assumption is for a lot of tests is normality. And so, for example, this histogram here, counts of a numerical variable, we can see that this is actually not normally distributed. I actually do it from a beta distribution, so this is actually right skewed because the tail goes off to the right. Whereas something drawn from, say, a normal distribution here will look something much more like this. And so, yeah, that statistical thinking of assumptions matter. You need to actually test assumptions. And sometimes that assumption is not straightforward. You have to, look at graphs. You have to look at variable. You could use QQ plots. You could even do formal tests like I think, Shapiro-Wilks test. But ultimately, it comes down to, discerning whether the assumptions are met or not, and then proceeding from there. And so that's, another piece of statistical thinking of assumptions matter and you need to test them, whether it's through graphs or through other methods. All right, fourth one is the perils of confounding information. And now in statistics, confounders, variables that are confounders, have a more technical meaning. But here I'm just speaking a little more loosely of like anything that might confound your analysis if you're not considering it. That might be variables, that might be the fact that there's missing or outliers, etc. But a good graph for this is going to be the group scatter plot. And in fact, I'm going to be talking about a famous failure of inference if you don't look at, all the relevant variables. It was something called Simpson's paradox. So Simpson's paradox is that, if you look at, say, a scatter plot, and in this case, I did draw a best fit line using a linear model. We see that these two variables look to be positively correlated, but that's actually not taking into account the fact that these are actually come from three different groups. And actually, if you compare them and you separate them by group, it actually turns out that there's actually a negative correlation in the group when you consider groups, that actually as variable one goes up, variable two goes down if you consider group things. It just turns out that sort of the average level, sort of the starting level of each group was different. And so that's a complete reversal. That's why it's called sort of the paradox. It's like, well, if you looked at it one way, which is like merging all the groups together, it looks positive, but if you actually consider group information, it's negative. So things like that. And again, other examples I mentioned, like outliers, missing data. If you're not considering that, you're not considering what could maybe be weakening or strengthening your relationships, you're going to get into troubles. And so be able to competently think about your data, competently include all the variables that are relevant, and of course, plot them to see how things change is an important part about statistical thinking. All right, and then finally, clarity. So clarity matters more than cleverness. So you want the point of a graph, obviously there's graphs that you just use yourself for exploration or, testing assumptions, but at the end of it, you usually have graphs that you publish with your results on posters and papers, whatever, to clearly show what happened. And you want to have clarity. You don't want to be focused on making them flashy or clever. You want to clearly get the information across. And so that's why something like a bar plot is a really great example of that. Now, I'm going to contrast that with a popular but actually pretty uh, unhelpful plot, which is the pie chart. Now, pie charts are easy to make, but they're actually hard to actually distinguish for typically the normal eye. And so I made this very simple. I don't have percentages or anything. I mean, you could add percentages, but then again, that's sort of needlessly complicated. Then why don't you just give the percentages? But you can see here, there's this, these are proportions or percentages across different groups. And actually, if you look here, you probably can't tell whether group A or B is the same or one's bigger or smaller, or even, you probably can tell that probably group B is the biggest, but it's actually not that easy. Whereas something like a bar plot, you know, where, again, I kept it simple. I don't even have axes. Now, in a good plot, you would have axes, and, if this was means, you would do error bars. These ones are proportions, so you wouldn't have that. You could actually see very clearly how the proportions are different. Group D is definitely the highest, and you can see A and B like right away. You can see, oh, A is slightly smaller than B. You didn't have to sort of peer and and sort of get muddled up by the difficulty of the the pie chart. So clear is really helpful. So choosing plots that clarify rather than confuse or abscond is a really important piece of good statistical method. All right, so that was very quick. I thought of helpful statistical thinking, and we previewed some common graphs that are pretty easy to put together. Hopefully that was useful. Thanks for joining me for this short video series. I will see you next time.